Let's continue Misao's lecture on data and perturbations. Okay, are you ready?
Yes, yes.
Okay.
All right.
Please go on.
Thank you. So, now let's start talking about delta n. This formalism is essentially based on so-called long wavelength approximation, or sometimes called the separate universe approach. Anyway, let me first start with linear perturbation, and I have to just tell you that there's no really theory of gravity or anything. It's just pure geometrical sort of argument, and that's sort of the essence of this formalism. So first, just a focus on some space-time geometry, which can be represented by a small perturbation of a Friedmann Lemaitre Bartolson-Walker universe. So you have this small fluctuations A, which essentially is in GR terminology, the fluctuation, the lapse function. So this 1 plus A dt corresponds to the proper time along the this orthogonal direction of the space-like surface. Now, the space geometry will be have this expansion of the universe. It's a square factor, and apart from that factor, you have some small perturbation in the longitudinal part, which I use this curly R, and the remaining sort of a diagonal part, excuse me, which can be decomposed into so-called the scalar part and the tensor part. Scalar is just a derivative of some scalar function. Tensor is by itself a tensor which cannot be decomposed into anything. It's transverse traceless. Here, for simplicity, I ignored so-called shift vector, which corresponds to choosing some different spatial coordinate. But here, for simplicity, I assume that the spatial coordinate is orthogonal to the hypersurface in some sense, to the leading order. Anyway, then in this slightly fluctuated space or the expanding universe. Actually, if you compute the three curvature, the curvature scale of this three-dimensional metric, then you find actually this this curly R represent the total three-dimensional curvature of the this hypersurface, if you can ignore these tensor components, and which I assume in the below. I mean, tensor may have small corrections to the curvature, but which is usually completely ignorable. So, most important component comes from the scalar longitudinal sort of a part of the metric perturbation. And because this sources, or maybe you can say this is a potential for the three-dimensional curvature on this T called constant three-dimensional space. So this is the reason why we call this curly R the curvature perturbation. But of course, it's maybe in more sort of a rigorous terminology, maybe I should call it curvature potential perturbation. So, one of the important things is that the value of this curly R doesn't mean anything. It's unphysical. It's the second derivative, you know, the Laplacian of the R, which has the physical meaning. Any questions? Okay. Now, another thing which is very important is that related to how the universe expand, and of course this is just A dot over A. You have some a perturbed expansion rate of this hypersurface, T called constant, and this hypersurface expansion is given by this 1 minus A term, actually, which actually corresponds to the difference between this proper time and the coordinate time, and plus a total derivative term, which is given in terms of this curly R and the Laplacian of the E. So this is the most important sort of equation. Once if you consider some metric geometry which is given in this form, then the perturbation in the Hubble is apart from this correction in time, the difference between the proper time and the coordinate time. The other part is completely integrable with respect to time. So this is the most important. And as I said, I mean, there's nothing, I'm not using any general theory of gravity or anything. I mean, this is just a pure geometrical thing. So as long as you have some four-dimensional geometry, which can be divided into space and time, then expansion of the space can always be written in this form. Okay.
Excuse me.
Yes?
Is the last equation the definition of the left-hand side?
Mm-hmm.
I mean,
It's tilde, you mean?
yeah, is this just the definition?
This is definition, the expansion of this normal vector. So if I can, yes, write it down. So it's if you assume this is vector n, this is the divergence of n divided by 3, I guess. Yes, this is the definition for any hypersurface. If you give a normal vector, oops, it's not so clear. Anyway, yes, then you take the divergence of normal vector. Okay, so that's the definition of Hubble expansion.
I see.
Okay, is it okay?
Yes.
Yeah. Okay, so then, oops, no, this I have to finish. Right. Now this is again nothing to do with a sort of a theory, but it's just a choice of gauge or choice of time slicing. As I said, if you assume that you have some four-dimensional geometry, space-time geometry, and you have the freedom in choosing time slicing, then you know this is kind of a choice of coordinate system. And in case of this the space-time which has a small, which can be represented by the small fluctuation away from homogeneous isotopic universe, you may have various, of course, there are infinitely many choices of gauge, but essentially there are only a few which are useful and important. And a couple of important sort of gauge here, essentially, well, I'm just focusing on time slicing because the spatial, well, I sort of fix the spatial coordinates. So a spatial coordinate, well, you don't have to, but it's quite, how should I say, not so important. The most important thing is how to choose the time slice. So focus on the time slicing. And one which is quite commonly used is called co-moving slicing. And this co-moving slicing means that oh, sorry, this must be 0. So yeah, and this is wrong. Yeah, this is 0, huh? Okay. This means that if you consider a energy flow of the matter, I mean, this is geometry, but you have some different energy flow of the matter. For example, you may have some flow which is something like this. Yeah, this may be a flow of the energy. Okay. Oops. Oh, no, the other way. Oops. Now, so if you assume this this flow is coincide with this normal vector, so you make the hypersurface such that the flow of the energy flow will be just orthogonal to the hypersurface, and this is it's a bit misleading terminology, but we call it co-moving slicing, and please don't get confused with so-called co-moving gauge. Yeah, maybe I should write it down here. So I say, yes, you have the so-called co-moving gauge, and this is a spatial gauge. This co-moving gauge means that for velocity, of this flow of the energy density, the I component, spatial component of the flow velocity is 0. So that this is the condition on, and this is the what we use. The terminology we use standard in cosmology comes from here. This everything is co-moving with the coordinate, and when everything is co-moving with the coordinate, then of course velocity with respect to that coordinate is 0. So this is co-moving gauge. Here this is co-moving slicing. So please don't get confused. Anyway, so with this, you can slice the space-time based on this condition, and if the energy momentum density is dominated by scalar field, like in the case of inflation, then this coincides with the slicing where the scalar field is homogeneous on a time slice. So in some sense, this means that the scalar field plays the role of time. Okay, when you have some monochromatic sort of evolution of the scalar field, then scalar field can be just used as a time, and that's the co-moving slicing. Another, which is quite important, slicing is the uniform density slicing. In the case of co-moving slicing, if this can be always defined if a universe is dominated by single scalar field, but as soon as you have multiple scalar field or maybe more different sort of type of matters come in and they interact and so on and so forth, then this slicing can be defined only at the linear order. At the nonlinear order, you cannot define co-moving slicing. However, at nonlinear, even at the nonlinear order, you can define the uniform density slice. This is easy. You just assume, or you take the slice on which energy density, yes, of the matter is spatially homogeneous. So, by the way, so this means actually, so you don't have any density perturbation by definition, but so it's always also be careful to differentiate the meaning of density perturbation from the all this gauge choice or maybe meaning of fluctuations. So what we call now, what we are dealing with here is the so-called. Oops, I should clear. So it's I'm focusing on the so-called scalar type perturbation, or just simply you call scalar perturbation. By the way, this scalar means scalar with respect to a three-dimensional space. So for example, from the four-dimensional point of view, this A is just the fluctuations of the G00 component, time component of metric. So it's a perturbation in the tensor, but a component. But from this three-dimensional point of view, this is a scalar. So this A is a scalar perturbation. Okay. Similarly, this E is a scalar perturbation. Curly R is a scalar perturbation. Okay. So scalar with respect to 3 dimensions. Anyway, so so you can choose either co-moving, especially in the case of single scalar field, or if not, you may choose some uniform density slice. And these two are most important slicing which you encounter in the discussions. And especially, so this, is in the case of radiation dominant universe, actually this corresponds to the uniform temperature slice, and which I have just discussed, just somewhat before. Where is it? Oops, how do I go back? Yeah, right. Oops. No, the other way. Yeah. So this slice, represented by this red slice, where the temperature is constant. This essentially is equal to a uniform density slice. And the point is that if you only focus on large scales, and if you have this uniform scalar moving slice, if you can define a moving slice when some single component dominate the universe, these two, uniform density and co-moving, essentially coincide. So that's another very important property from matter point of view. So of course, I mean, this is only on very long wavelengths limit. So as soon as it comes to a small scales, then there will be these two will be different. But on large scales, the difference between these two becomes small and small. Okay, so that's the sort of matter-based gauge or matter-based slicing. Another is the instead of focusing on matter, you can focus on the geometry-based slicing or geometry-based gauge, and one which is not so much used in the perturbation theory, but as soon as you come to as a nonlinear, for example, numerical relativity computation and so on, then most often used slicing is called uniform hub slicing, where the expansion rate of the universe is uniform on the slice. Of course, it depends on time, but it's uniform. And this gives you this condition. This is the condition for the uniform Hubble slicing. And another is the flat slicing. This, as I said, this curvature perturbation is the potential for the three-dimensional curvature. And then if you choose a slice in which this curvature currently is zero, then the three-dimensional curvature is essentially zero, apart from this small correction from maybe tensor type perturbations. So this gives you the flat slice, and which in some sense minimize the effect of geometry, the effect of deformation in the geometry. So any theories, if you just write down some equations of motion for matter field and so on and so forth, if you write it down on this flat slicing, then the equation looks most similar to what you would find in sort of a flat Minkowski space. Okay, any questions? It's okay. All right, so another thing which is, so as I said, the uniform Hubble slicing is, it's not so convenient on at the linear level. I mean, it's not so useful, but it's very useful at the nonlinear level. While at the linear level, most useful one is either this flat slicing, and the other is the Newtonian or Newton's or shear-free slicing. And this slicing condition assumes that the scalar part of the a traceless part of the metric is zero, and so essentially this gives you a geometry. So you don't have this. So three-dimensional geometry will be just proportional to the a flat. So conformal, maybe you could say conformal to flat metric. Okay, and so in the case of now, this is in the case of general relativity, but in the case of general relativity, you can easily show that this, as I said, co-moving slice is essentially equivalent to uniform slicing, uniform density slice, and which coincides with uniform Hubble slicing. And this actually is again essentially very close to this local Friedmann equation, because as I said, in the very early universe, this term and this term dominates, and the curvature term is essentially ignorable, which means that any small fluctuations in density is reflected in small fluctuations in the Hubble parameter, or if rho is uniform, the Hubble is uniform. So that's how these two geometry, that's why you have this equality, essentially equality on the very large scales. But of course, so as soon as you consider some other theories of geometry, gravity, then because the relation between all these, definitions may become highly non-trivial. So you may not have this inequality even on large scales. So again, in most cases, this is true, but there are several models of gravity which violate these conditions. Okay. Now,
can I ask a question?
Yes, sure. Yes.
I missed something, but since when you neglect this zero I components of the?
Oh yeah. This is So I just simply assume that the spatial coordinate will be just along the orthogonal vector. Okay.
So it's just you assume that this normal vector of the
the x in a spatial coordinate constant line will be just coincide with the normal vector, because spatial coordinate doesn't play any fundamental roles, and you can always choose this, and it doesn't affect anything. So just to make it simple. Of course, you don't have to. Okay.
Okay. Thank you.
Is that okay? Mm-hmm. All right.
So I have a question.
Yes, sure.
So I just want to know the reason why some gauges are impossible when you consider the nonlinear order.
Yeah. But for example, so this the whole point is that when you call the time slicing, it must be a slice, huh? I mean, you may always write down, for example, the condition for this, but this condition can define some vector, yes, but this vector will not be a normal to hypersurface. Namely, if you take the derivative, you have the sort of a rotation part, it comes in. I don't know exactly how to express this, but this is a pure geometrical thing. The vector, if you may have some vector field, but not all the vector field are normal to some hypersurface. Understand? To have hypersurface, T equal constant hypersurface, the normal vector must be normal to that hypersurface, right? So any condition must define normal vector of that hypersurface. But this condition, well, this was zero, sorry. The condition doesn't define a normal vector in general. Okay.
Thank you very much.
Yeah, and similar to actually the case of Newtonian slicing. So this condition is okay at linear level, but at nonlinear level, actually, this involves some dynamical degrees of freedom, and you cannot really do it. So you have to be very careful with the Newtonian slicing. This is true only in certain limited cases, or maybe limited situations, if you go to a nonlinear order. Flat slicing, as I said, as far as this sort of a longitudinal part is concerned, if you divide the metric into a sort of a longitudinal part plus some non-longitudinal component, then you may always be able to define this the three-dimensional curvature as written in terms of two terms. The one comes from this sort of a longitudinal scalar component. The other, I will have some expression of this later somewhere. But anyway, so in that case, you may take this slice even at nonlinear order to make this sort of a longitudinal part of the a component of the three-dimensional curvature to be 0. This is sort of related to the conformal decomposition of the geometry, but so that's a possibility. But it may not be so convenient at the fully nonlinear level. At fully nonlinear level, this from geometrical point of view, this uniform of slicing is clearest slicing condition. Okay. And in the case of the matter-based slicing, uniform density, this you can easily see it's always possible, unless of course a fluctuation in the density is so high that this hypersurface definition of the hypersurface no longer satisfies the space-like condition. So that's an extreme case, but otherwise this can be easily chosen at nonlinear level. Okay. Any other questions?
Sorry, short question about the flight slicing. So do we still have the tensor perturbations in this gauge choice?
Yeah. Well, yeah. So uniform density slice. This is just the as I said, it's a scalar thing. I mean, from three-dimensional point of view, and you can always define this independent of a tensor perturbation, right?
Oh yes, sorry, I mean for the flat slicing. Yeah.
Oh, flat slicing, yes.
Yeah.
So as I said, you can make the conformal part of the metric to be flat.
I see.
So
tensor, there are still gravitational waves.
Yeah. No, if there is some tensor or some non-trivial sort of a skewness, which corresponds to this kind of degrees of freedom, then you will have a non-trivial component, and which you cannot put it 0. So this flat actually becomes like with quotations, and flat, just the longitudinal part is flat.
I see. Thank you.
Yeah. Okay. Now,
excuse me, may I ask a question?
Sure.
To better understand about this gauge, let me make sure one thing, because the matter sector and the geometry sectors are connected with each other through the Einstein equation. So is there any special relation between those two ways to fix the gauge in the matter sector and geometry sector?
So are you saying that, for example, can we choose a gauge which sort of combines these two, matter and geometry?
No. Just I wonder if there is any equivalence among some.
Oh yeah. Oh sure. Given some theory, probably yes, you can. But because you do have the Einstein sort of equations, huh? But I'm not exactly sure. So far as I know, no, at linear level, of course, but as soon as you go to non-linear level, I guess probably it's very difficult to define the equivalent gauge from matter point of view and geometry point of view. Essentially, they are different. Yeah. Okay.
I see. Thank you.
Yep. Okay. Now, this is now again, I'm just writing down the part of the Einstein equation now of the 0 component in the sort of form of the Friedmann equation. So if you write down this under this perturbation condition, yes, which I gave here so any choice of slicing, I'm not choosing any slicing here at the moment, then you find up to the order epsilon square. Epsilon is the ratio between the horizon size to the wavelength. So, or maybe just a one spatial derivative. So this Laplacian will be epsilon square. And if you ignore the epsilon to the fourth, then up to epsilon square, you have this 3h squared minus this Laplacian r equals 8/0. So this resembles completely the if you remember, maybe I have it after this Friedmann equation. Huh? It's very it's just the multiply by 3 on both sides. Then oops, then you have this. Huh? You have this. Now, but the difference is that, of course, this curly R may depend on time. Yeah, I'm not, since I'm not using any gauge or any equation motion or anything, this may depend on time. Then behavior of this equation, although it looks quite similar to the Friedmann equation, can be quite different because in the case of Friedmann equation, this space time dependence must always come through a square, and this does not depend.
May I ask a question?
Yeah.
So this is written without choosing gauge?
That's right.
Thank you. Yes.
Yeah. Mm-hmm.
Thank you.
Yeah. So that's a very important point. I mean, it has exactly local Friedmann form, but it doesn't mean that it actually satisfies local Friedmann equation, because this may depend, curly R may depend on time. Now, but even if it doesn't depend, actually, on the sorry, in the very large scales in the early universe, as I said, essentially this term is a 1/8⁴, and so they have the parameters essentially dominated by this density, and this is just 1/8². So if you go to the early universe, then any sensible theory of initial condition can give they can be just give you a very, very tiny infinitesimal small initial condition for this. So at the early time in the universe, epsilon can be epsilon square is already very, very small. This term is very, very small. So if you ignore that term, then this 3h squared equals 8/0. This is the Friedmann equation. At this level, this holds irrespective of the this choice of gauging. I mean, if your perturbation is at linear order. Okay, so this sort of assumes that if you want to compute something at leading order of the gradient, we call gradient to expansion or long wavelength limit, then this guarantees that so-called separate universe approach is okay. Okay, so this is,
sorry, would you please show the definition of H tilde? You are working in long wave limits, so then probably the definition would simplify H tilde.
No. So maybe I should write it again. So you have a normal vector, okay, n, right? And you take the divergence of n, yeah? You have some new here, maybe here, something like this, okay? So,
yes.
So this is defined to be, I think, 3h, okay? All right, 3 just is because it's 3-dimensional, is spaces. So, but when you talk about the expansion rate, we talk about the expansion rate of the length scale. So that's why h is defined like this. This is the essentially fully nonlinear definition, but here it's tilde because this has some perturbations. Huh? This is perturbed. Okay.
Yes. Yes.
Okay.
And this equation, this first equation, this slide, this is just hold in linear perturbation.
Yeah. So far it's a linear theory. I will come back to the nonlinear case later, yes. And in that case you do need a little bit more conditions. But anyway, at linear order, this is always the case.
Yes, and H tilde includes some linear perturbations.
Oh yes, that's right. Yes. This includes the linear perturbation.
I mean,
like this.
Yeah.
Like here. This is so in terms of the those geometrical. This yes. Is the expression. Yeah.
And the last expression goes away in long wave limits or not?
This one.
This last one. Just last one. E.
Oh yeah. Yes. This I will use later. Yes. It's a very important point. Yes. Yeah. I'll come back to that later. Yes.
Thank you. I'm sorry.
Yeah. Okay. No, it's okay. Thank you. Thank you for your question. Okay. So, but as I said, I mean, if this curly R is independent of time, then even up to epsilon square, you have a Friedmann equation. I mean, in some sense, you have the exact Friedmann equation, including what do you call the spatial curvature term, right? So, by the way, let me just clear. Okay. So this, if curly R is time independent, then Friedmann equation holds up through the epsilon square term. And with this a sort of a local curvature, which I mentioned some time ago in this morning too, will be related to this curly R by this formula. So the K will be just apart from this the small prefactor, the negative sign and so on and so forth. Anyway, it's essentially Laplacian of the curly R. Yes. Okay. So this tells you, since the Laplacian is small, already very small, but they still even if you want to include that small corrections, you can still have a Friedmann equation. So that's the case when the curly R becomes time independent. And I will, well, there are some slight mismatch in the lines, but anyway, the so-called this curly comoving slice, or as I said, it's a comoving or uniform density or uniform Hubble slice. Either any is okay, but on those slicings, we will find later that in adiabatic limit, this curly R becomes constant in time. It's only space dependent. So in this case, actually, you can exactly recover the local Friedmann equation, including the curvature term. And actually, this property remains the same to the nonlinear order if curly R is still properly defined, and you can show that in a certain slicing, I use this uniform density slice. On uniform density slice, the curly R becomes constant in time. Okay. So with this, the perturbations, now I will compute the delta n, and well, since delta n, a number of E-fold is the a number of expansion, E-fold number of expansion, it essentially, by definition, is the integral of the expansion rate along, say a normal vector, and the whole point is that this perturbation expansion rate has this fluctuations contribution from it takes time. This Raps function, but because the proper time has this 1 plus a contribution, actually they cancels when you take the product. And actually, this is true for full nonlinear order. But in any case, so this a product of h tilde times d tau cancels out this perturbation in the Raps function, and the remaining part only comes from this total derivative, time derivative term. Then, so the whole delta n from if you compute delta n, again, I'm saying that this doesn't depend on any choice of gauge. Just choose arbitrary gauge or slicing. You can compute this delta n between these two. So this is at this level still a coordinate dependent or gauge slice dependent quantity. But anyway, the important point is that this will be given by, I mean, it can be totally integrated, yeah, totally. So so it's this delta n is just the difference between the initial value and the final value of this quantity. And as the early correctly just mentioned, that this Laplacian will be small in the leading order of epsilon. So if you ignore this epsilon square term, then this difference in number of e-fold will be the difference between the curvature perturbation in the final slice minus the some value at some time t. Okay. So this is essentially the most important equation. Okay. Right. So for example, I mean, so this is something. I mean, I'm just drawing some you know, different, what do I mean by this delta n and so on, and depends on the coordinate choice, I mean slice choice. For example, if you, for example, this, look at this the black hypersurface, which we assume to be a flat hypersurface where the curl is 0, then and then if you compute the delta n between these slices, by definition these two just vanishes, so this is 0. So apparently, as you see, this is a gauge dependent quantity. So this is just purely given in terms of slicing. So by itself, it doesn't mean anything. Okay, it's just a pure geometrical thing, and depending on your slicing. So there's no physics here. What I mean is, okay. Okay. Now, but then once you fix the gauge, of course, there's some quantity which is under the fixed gauge condition may have some physical meaning, and sometimes may be very important. And one of the choices is this. So let us choose the initial slice to be flat, flat slicing. And this is what we had in, for example, in this, you know, the explanation of the inflation. I told you that in the beginning you can assume that you have some essentially part of geometry and the fluctuation in the scalar field. So that's kind of it's a slice you choose as an initial slice or at time t. The final slicing, let's choose it co-moving, okay. And so this will be similar, or maybe I changed the color. So but anyway, this will be the slice on which the temperature of the universe will be uniform. But you have a small fluctuations, non-trivial fluctuation in the curvature, and this curvature perturbation will be constant in time. Actually, which I will show it later. I mean, again, it probably depends on the theory of your gravity, but and everything, but in at least in GR, in the adiabatic limit, this becomes a constant in time. So and as I have just shown you, that slice is special in the sense up to the epsilon square order. Actually, the Friedmann equation is valid on that slice. But anyway, so as for now, if you just assume when you compute delta n, you always choose the initial slice to be flat and the final to be co-moving, or maybe uniform density, it's the same thing. Then, by definition, if delta n is the difference between this curl, but the final one will be the curvature perturbation on co-moving slice. The initial one is on flat slice, by definition it vanishes. So you see that delta n just gives you the curvature perturbation on co-moving slice. Okay. Right. And by definition, if you, for any t, you choose the initial slice to be flat, then it's t independent. So this is the quantity which, and if this is conserved afterwards, after this time, then, well, you know, you can essentially compute delta n up to any a distance back in time and take the flat slice, and if you can compute the fluctuations in delta n, then that gives you the final answer for the curvature perturbation. Okay, right? And it's quite often they people use theta for this Curry RC. It's okay, but I'm reserving actually sometime later. I probably use this for the uniform density slice quantity. I mean, it doesn't matter, but sometimes it's nice to just reserve some parameters in case you need it to show some differences. But anyway, for the moment, they are essentially the same, apart from sometimes negative sign, so you have to be careful with the definitions. By the way, so my definition of the curvature perturbation is that well, it doesn't matter whether you use the curly R or not, but as a variable, but it's important that he has a plus sign here. Okay. Sometimes people might use minus sign there. So that's why there is sometimes confusion. Okay, so now let me go to some simple example and single phase slow inflation, and then this is very easy to understand. I mean, from this because everything is in some sense adiabatic from the beginning. So from the beginning, if it is adiabatic, then it does independent of the say how to say? Oh, sorry, no. The curvature perturbation on convening slicing on super Harpur scale is always constant in time. Maybe I do have to show somewhere, but sorry. So this is the result of the Einstein equation. But anyway, so once you know this fact, then you can just compute that at any choosing at any epoch as the initial time. The most convenient time is essentially in the case of inflation, as you say, that you have some uniform, essentially a almost constant Hubble horizon, and after the end of inflation, it starts to expand faster, usually like 8 square, where this is just a comoving size which behaves like a scale factor 8, and as soon as fluctuation scale goes out of this Hubble horizon, the curvature perturbation on comoving slice becomes constant in time. So you can choose any time as a final time or initial time. So the what you can do it's most conveniently, for example, in the case of single field slow model, you choose the end of inflation to be the final epoch, final time, and the horizon crossing time to be the initial time. Okay, the difference that the final time will be chosen as comoving, and which is exactly what you should choose, because the any transitions from say vacuum dominance to radiation dominance and whatever is determined by the value of the scalar field. So which means that the uniform scalar field slice coincide with uniform curvature comoving slice. Anyway, as for the initial slice, as I said, you should choose flat slicing, but fortunately, the flat slicing is where it's most easily you can easily compute the fluctuation in the scalar field. So which I just write it in like delta pi. It's F. F means the fluctuation flat slicing, and this by some quantum field theory computation or anything, but you can easily do, because on this slicing at leading order you can completely ignore the effect of gravity, so you can just compute the fluctuations as if space is just flat but maybe expanding, and then you compute the amplitude of this at the horizon crossing. After horizon crossing, we know that the curvature perturbation is conserved, and this gives you how to compute delta n. So, for example, let me just write in this way. So, let us just, for the sake of a computation, I mean, so usually, as I said, you compute the fluctuation phi in the flat slice, but let us prepare some co-moving slice near the slicing, where the delta phi is 0, but you have non-trivial curvature perturbation. So this will be a change in the spatial slicing. Now, and these are two conditions. Now, by definition, if you start from flat slicing and this difference in the time, which of course depends on space, this is the sort of a gauge, a parameter, huh? So if you add this delta t f to c, yes, questions? No, it's okay. All right. So if you add this delta t to the flat slicing t called constant slice, then you should end up with the delta phi equals 0. So this means that on that slice, oops. Oh yeah. Well, yeah. So if you expand to the next order, then yes, this on that co-moving slice, a scalar field must be uniform, and this determines the relation between this delta t and delta phi. Yes, because delta phi must be absorbed into delta t. Okay, and the curvature perturbation on this co-moving slice is, as I said, it's just given by in terms of delta n, which as I have shown, without any theory and so on, it's just definition of delta n in some sense. This is essentially this h delta t from flat to co-moving. This is a gauge a transformation. Yes, but this transformation delta t is given by this equation, so you can and phi dot can be it becomes in the denominator, but you rewrite this dt of d phi, assuming the phi is dominating our universe. This is single field slow roll, and phi can be used as a time, as I said. So this uniform phi slice can give you a time slicing. Now, so this essentially is, if you look at the original definition of n is the number of efforts counting backwards in time. So this means that dn is minus Hubble times dt. Now, here you have this minus Hubble times dt. So this actually is dn over d phi multiplied by d phi f. So that's the end of the story. Now you see that the curvature perturbation you want to compute actually can be represented by delta n, which can be actually computed from the derivative of number of E4 with respect to the value of scalar field. So as soon as you know the function of n as n as a function of phi, then you can immediately compute this part and you can get the final amplitude. And this delta phi f can be computed, as I said, by some quantum field theory computation. So this is the delta n formula, which was intuitively first sort of derived by Stravinsky in '85 paper. So anyway, the important point is that, so what you have to compute is the fluctuations of scalar field inside the horizon. And as soon as it goes out of horizon, you forget about any fluctuations, a perturbation equation, anything. You just, only thing you have to know is the background equation, the relation between n and phi. And if, as soon as you know how n is given in terms of phi, then you can compute the final curvature perturbation amplitude. This is the delta n formula at the linear level. Okay. Any questions so far? Is it okay?
Excuse me.
Yeah, sure.
Yeah, so this TH, so these two slices are on the same time, TH?
Yeah, that's right, that's right. Yes, that's right. So, yeah, as you say, you fix some time, yes, time, yeah. But for the same time, you have different slicing, huh?
Yes, so then this delta n looks like time dependent. I mean, if we have th prime something.
Yeah. So that's what you think, and actually so this derivation here actually is focused because it's the curvature perturbation is moving curvature perturbation constant in this single field case. I'm using that fact, so it's kind of cheating. Yes. So in general, you cannot actually write in this form, but what I'm trying to say is that so delta n actually is intrinsically just given in terms of the dn d phi delta phi, and as I said, as I defined here, actually it is independent of initial time t, right? By definition. Okay.
Okay. Yeah. Okay.
All right. So but of course, I mean, so that's why this is the final. Yeah. But in the current case, actually, this final is equal to this Currier here. Yes, RC.
I see.
Yeah. I mean, it's just a coincidence. I mean, I know because the Currier RC is conserved. So this is a bit of cheating here, but the whole point is that the reasoning that the Currier C can be given in terms of delta n, and delta n can be computed by this initial slice, fluctuation in the initial slice, in the flat slice, is true. Yes, and here you don't need this, but the important point is because of this, you see the if you know how say if you know how to compute the fluctuations in number of E-fold, given the fluctuation some scalar field or something, then you can always compute the final curvature perturbation amplitude. So this is not true in general, but this part is always true. Huh? This part is always true. Okay.
Okay. Thank you.
Yeah. So that's the reason why, I mean, you can easily sort of extend to multi-component system. And so what is important is the number of E-fold. Maybe I should write it down in more explicitly. Okay, so maybe I should write something like, okay, so yeah, so delta n, delta n actually is, so n, so it's let's say phi plus delta phi minus n phi, huh? Oops, phi. Okay. So this and so this will be the sort of a total expression, and here we are just focusing on the linear perturbation. But once you understand the reasoning behind this, then you can easily see that this can be easily extended towards nonlinear level. Okay. So at the leading order, you just once you know the how number of E-folds related with as a function of phi, you can easily compute, and this computation, this derivative of n with respect to phi is computed on the background homogeneous universe trajectory. Okay, the only inhomogeneity computation comes through this delta phi f computation. But if you assume all these scalar fields, let's say canonically normalized and so on and so forth, then it's very easy to compute this part. which I'm doing here. So let's say so if you just express this in terms of this derivative of n times the fluctuations in the scalar field in this some n-dimensional scalar field space, then you can easily compute the power spectrum, which is given by this PSK. This S stands as just scalar, and this 4 pi k cube divided by 2 pi cube is just a phase volume. So this total quantity is a dimensionless sort of amplitude of perturbations, and so this can be just computed by taking square of this, and so the one part comes from, if you assume that delta phi is independent from each other, and each fluctuation is essentially given by those vacuum fluctuations of the h over 2 pi. Sorry, I didn't exactly talk about this, but this is the quantity you would obtain for some any type of scalar field fluctuations, as long as their mass is sufficiently lighter than the Hubble scale during inflation. So in this case, you just the amplitude is known, this and this dn d phi square is also known. I mean, once you know the function n as a function of scalar field. So and then you compute this and you find this, and then you can sort of have some inequality because the Hubble square essentially is now again going back to the definition of n. So Hubble is given by dn d phi, so phi dot. So Hubble square is this phi dot dn d phi square, and this is this inequality, the famous inequality I forgot in mathematics, huh? Square of some the product is less than the square of each components, huh? Schwarz inequality, was it? Yeah, but anyway, so then you immediately find that dn square will be greater than h squared divided by phi square, and which give you this. So you have some lower bound. I mean, given this, if this assumption is correct, on the amplitude of the scalar perturbations, yes, in this form. Usually in a single scalar field case, this is equality, this is just phi dot square, okay? But when it becomes full many multiple component, then this is an inequality. So knowing this phi dot doesn't exactly give you the final answer, but you should know the number of efforts as a function of the scalar field, okay?
So can I ask one question?
Yeah, sure.
So in the previous single field case, you identify the time t as the function. You identify the time as the same as the field, right? But in the multiple case, how do you do this?
No, you cannot do that. No, that's right. So that's another. I mean, at the linear level, yes, you can. You may be, but since I'm going to discuss things at the nonlinear level, for the moment, maybe you can regard this as the final sort of a hypersurface to be, say, uniform density, not just comoving, okay? I mean, the comoving density is defined only at the linear level. At nonlinear level, this you cannot do, okay? But so for the moment, it's a linear, so linear, it's okay, all right? It's okay? Oh yeah, by the way, so the way I forgot to mention a very important point, huh? So as you could, as I write it here, actually the curvature perturbation on comoving slice, yeah, is, as I said, it's a conserved in the case of single field slow inflation, but it will not be conserved at all yes, at all, and even there are multiple components. This is a very, very important sort of yes, property, and which is again, which is the reason why the delta n becomes so useful in the case of a multi-component scalar field. In the case of multi-component scalar field, delta n tells you that if you only need to know background, yes, this background equations. It's okay. Somebody is trying to say something. Is that okay? Oh, okay. So you only need a background motion. While if you want to solve this, then you have to solve the full linear perturbation equations, and which can be quite complicated when you have this multi-component scalar field. So it takes some time, and then you may be able to compute this final curvature perturbation by integrating this equation for the moving curvature perturbation. But this delta n formalism tells you that you don't have to do that. That's useless. I mean, the only thing you have to know is the background equations motion. Okay. Is it clear so far? Yeah. Okay. Now this is just a little bit more about this. Not much to do with the delta n, but just for the sake of some maybe advertisement of my very old work with Ewan Stewart. Is that so in this sort of a fairly simple case of a multi-scalar field in say some canonical scalar field case, then total amplitude of the scalar perturbation, which is essentially what we call the curvature perturbation spectrum, will be given in this form. The square of the nabla n times h squared divided 2 pi squared. On the other hand, the tensor spectrum is essentially the same, but with this is the 8 by g or 1 over m Planck square, and with some certain sort of a normalization factor times this h squared 2 pi squared. There's a famous sort of you call consistency condition in the case of single field case, where the spectral index of tensor field is related to this so-called epsilon parameter of the scalar perturbation or the expansion of the universe, the Hubble expansion of the universe. Anyway, so this is just using the Einstein equation. So here I'm assuming Einstein equation, Einstein gravity as it says here, and in this case you have some smallness parameter comes which is related to the small tilt in the tensor spectrum, and because this is, as you could see, always positive, and t is always negative, meaning that the tensor spectrum always slightly red tilted. So that's a very, very general result for the Einstein gravity. Now, again, if you use the definition of n, which is h equals d minus dn dt, which is just the derivative of n multiplied by phi dot. And if you insert this here, then you find this will be, and using again this Schwarz inequality, this will be greater than this quantity, and this quantity is, if you look at this initial expressions, is just a ratio. This is the scalar to tensor ratio. Scalar to tensor ratio divided by 8. So when you have multiple scalar field, and if you have sufficiently, say, large amplitude of, say, so this means that you need some finite amplitude tensor perturbation, and your observational data is accurate enough to so that you can sort of read off a spectrum tilt, then this tells you that the tilt must be greater than PT over PS divided by 8. So, or maybe this is the final. So this, and if this is equal, it means that this is a result of a single field Slorlov model. But whenever this inequality is violated, then this tells you that you have more scalar field. Okay, and actually, you can easily generalize to most of the theory of modified gravity theory, and the most modified gravity theories, actually this holds consistently, and the reason is fairly simple, because when you talk about scalar perturbation spectrum, the scalar perturbation spectrum has the contribution from many different degrees of freedom. Yes, which is contained in this. You have the many dimensions of different directions of the derivative of n. So which gives you all the different directions, degrees of freedom. So essentially, if you have a small n degrees of freedom in scalar field, then you essentially multiply the amplitude of scalar field by n. While the tensor only has 2 degrees of freedom, and it remains 2, unless you have some very funny theory of gravity. So the tensor perturbation amplitude remains the same, essentially given in terms of this Hubble parameter during inflation. But the amplitude of the scalar perturbation can become large depending on how many scalar field contributes to this scalar field perturbation. So that's why once you increase the number of scalar field, the ratio between tensor to scalar will decrease. Yes? So that's the reason why you have this inequality. Okay? Any questions? Okay, so now I have to go to the nonlinear order, but maybe because of time, I'm not exactly sure if I should go into the next section.
Misao.
Yes?
Question.
Yeah, sure, please.
Now, taking the current observational data,
yeah,
can you draw any conclusion about number of scalar field?
Unfortunately, no, because currently we're not seeing any amplitude tensor perturbations. So, which means that so this left-hand side actually is not measured. We know it's smaller than something. Yeah, that's all we have, and it can be very, very small. So this actually means that currently no multi-component scalar field model is excluded. Essentially, everything is allowed.
So in order to obtain the value tensor spectrum, so what kind of things should be measured?
Oh, so this is what the so-called, for example, this is the project which is right now going on, is Lightbird project and so on, is aiming for that the tensor perturbation, like in the case of scalar perturbation, you have a non-trivial kind of a gravitational potential, which gives rise to gravitational potential, which gives rise to this fluctuation, the CMB temperature. Yes, but now the tensor perturbation gives you a similar sort of fluctuation CMB, but it's always so-called B mode polarization. Excuse me. No. So you have 2 degrees of polarization in the case of electromagnetic waves, and one you can decompose it into sort of an electric type and magnetic type. In some sense, the electric type is even parity, magnetic type odd parity. So in a rigorous sense, it can be defined only if you have the whole sky data. But anyway, if you do some sort of multi-component decomposition, you can assign each components to some so high multi-component fluctuation in the sky, and this B component a polarization fluctuation can be only induced by a tensor perturbation. I mean, primordially tensor perturbation. Locally in the current universe, actually this is a big problem, but there are lots of sort of contaminants which can produce those B mode polarization in the CMB. And the most important sort of observational task is to clean or get rid of all these sort of unwanted B modes and to single out the B mode from the very early universe. And this is the project, for example, LightBar is trying to do. And if they do it properly and we are lucky enough, then within 10 years or so, around 2030, we will have this result, the result on PT over PS.
I see. Okay.
Yeah. Okay.
Yeah. Thank you.
Yeah. Okay. Any questions for so far? Anything? Anybody has any questions?
Can I ask a question?
Sure. Yes.
I want to see this slide for the delta formalism in single field theory.
Yeah. Is this one?
Yeah, there is a tricky part that the RC is defined on the final slides, but later you calculate everything in the horizon crossing time.
Yeah. Because as I said, so I'm just cheating. Using this relation.
Using this conservation. Yeah. But later you said that in the multi-field theory you do not have the conservation of the curvature perturbation on super horizon scales. Then how do you do that?
Yeah, but so this is kind of a maybe I shouldn't include this, but forget for the moment. Forget about the this single field case, okay? And as I said, okay, so let me as I said, well, this is the definition, right? Yeah. Now the question is how you compute delta n. So what's the meaning of delta n? But I said this is a number we for two the initial flat slices. So you have some flat slice, you have some co-moving slice, yeah, and then you compute number v for that, and the difference between these two will be delta n. Now, what gives rise to this number v4? This is just a fluctuations in the scalar field, right? Because n is a function of a scalar field, right? So I mean, well, actually, you do have to show this number v for the fluctuation actually can be computed in terms of a background quantity, but well, intuitively it's very clear, right? As I said, since the Friedmann equation, the local Friedmann equation is holds for any type of slicing. So so this means that you may be able to compute the number of for the function of phi even in how to say deformed a universe, that slightly perturbed universe. And the point is that so each sort of for each trajectory you can regard this as one single universe with certain say curvature perturbation, and this is a universe with other curvature perturbation, and so on and so forth, right?
So this delta means that you compare for the number of two different or separate.
Yeah, that's right.
Points.
Yes.
A separate universe kind of.
Yeah. That's exactly. I mean, so which means that this delta n is a function of a space point, right?
I see. Okay. Then I can really understand.
It's not so clear. Sorry. Yeah. Is okay?
Yep. Thank you.
Yep. Anyone else?
One more question. how do you calculate the delta phi f?
Yeah, so this I didn't have much time, but okay, let me go back to the very beginning. Where is it? Oh, this takes time. Yeah, here. So this is a very how to say a naive way of writing, but essentially you have this 0-point vacuum fluctuation, and here I'm just writing the equation motion, but actually you have the action. You compute the fluctuation amplitude, and you can take the mean delta phi square value, and these quantity fluctuation can be computed most conveniently on this flat slicing, where you can at leading order ignore the effect of gravity, just apart from the expansion of the universe. So, so then you just compute this delta phi, okay?
Okay.
Is it okay?
Yeah. Okay. Yeah. Thank you.
Yep.
Can I ask a question?
Sure.
Could you please turn to page 24?
Mm-hmm. 20. Oops. 21, 22, 23, 24. Yes.
Okay. So wait for a minute. Okay. So here, the first equation is dn d phi a. So is evaluated at which time?
Well, so as I say, the number of fluctuation in delta n, because the initial slice is flat, and
Yes.
the fluctuations always comes from the initial slice, essentially difference, but of the fluctuation initial slice. So this delta phi is the evaluated at the initial slice, initial flat slice.
Okay.
Yeah. So that's the point.
So how can I choose the initial slice? Just the one that moves across the horizon, or?
Yeah. Well, usually because unless I mean, well, in the standard case of inflation, it's essentially quasi exponential expansion. So if you go out of the horizon with for a couple of number of e-folds, then everything essentially freezes out. So in more precise computations, maybe you have to compute delta phi slightly after the horizon crossing. Yes, but
yes.
Because evolution of the delta phi during that, say, 1 or 2 e-fold is almost completely zero, or I mean, at least compared to the how say ambiguity in the scalar field model, ambiguity or the accuracy of the observations or whatever. I mean, it's that part is in most cases essentially very ignorable. So that's why you can, at the leading order, you can just assume to evaluate this delta phi at the horizon crossing.
Okay, so the delta phi formalism, delta n formalism cannot be extended to something inside the horizon.
There was some trial before, but they didn't succeed very well. Essentially, yeah, the whole point is that when inside the horizon means that the two spatial points can communicate each other, huh?
Yeah.
So which means that then the delta n becomes not only in the time direction, but it's spatially non-local. And this makes everything too complicated and useless. So by definition, if you have some flow, some equations, yeah, like this equation, which it holds along, say, constant spatial coordinate x. Yes, and if this will not be affected by any physics, just next to this x. You have something next to it, but the assumption that this anything which is going on in next door cannot affect this, and which means that the size must be large enough so that there's no causal communication between two patches.
Yes.
Right? Yeah. So going inside the horizon loses that information, and then it becomes so terribly complicated.
So that means inside the horizon, the perturbation evolution can only be solved by solving the equations, solving the first order equations.
That's right. That's right. Oh, by the way, when we talk about this a horizon, it can be so-called a sound horizon. For example, if the sound velocity, any propagation apart from gravitational waves, and which we sort of here we're ignoring, as far as the scalar field components are concerned, or scalar type perturbations are concerned, if the sound velocity is very small, then the size of the sound horizon becomes comparatively small.
Yes.
Then this kind of a sort of a separate universe type approach that the next door effect will not be next door physics will not affect what you are solving is valid until a sound horizon.
Oh, okay.
Yes. If CS square is small, then you can go down to smaller scales. Yeah. So, but that's a very, very special case, which doesn't happen very often.
Okay. So thank you.
Yeah.
All right. There are many questions. I think I have to interrupt this moment.
Okay.
So I'm going to take only one more question. Okay. After that, I would like to close today's session. Any question? All right, then I have one quick, very simple question. The reason we do this is to understand the origin of inhomogeneity of our universe, C of inhomogeneity. And the answer here is the quantum fluctuations, basically. But this quantum fluctuation assumes homogeneity before the quantum fluctuations, right?
Even the fluctuations statistically homogeneous? Wait, what do you mean homogeneity?
You assume the background is homogeneous.
Oh, yeah. Yes, and, yes, that's right. That's right,
but,
yes.
But we don't know whether our universe started from the homogeneous
objects
or not.
That's right. That's exactly why I said originally inflation was to solve such homogeneity problem and initial condition problem and so on. But actually it didn't. Okay, inflation doesn't solve such problems. It's still an assumption. But under that assumption that the universe is homogeneous in the beginning, yes, and there is, for some reason, I don't know whether it's singular or not, but anyway, it started somehow. Once it started, and once it starts inflating, then everything you can predict everything, especially the amplitude of the fluctuations and the tensor perturbation, everything, and you can compute them and you can compare with observation. So fluctuations are the most important point. Yeah.
So observational results so far agrees with this setup.
Right. But as you correctly point out, I mean, inflation doesn't solve homogeneity problem. This is something sometimes quite often misunderstood, but it's true. Yeah.
Okay.
It's an
then,
assumption.
Is there any work that assumes the initial background space is inhomogeneous? Before the quantum fluctuation.
Yeah.
So
there are several works. I mean, this is mainly the reality is done by Zvi Plan. Yes, he did some numerical computations, and they sort of showed what kind of initial condition, sets of initial condition. So you have to explore the initial condition space, and what kind of initial condition space would lead to inflation and not or not, and so on and so forth. But so it's, and you have some kind of a naive, has a qualitative understanding of how homogeneous the initial state should be, but of course there's no real sort of a theorem type things at all yet.
Okay, all right. That's the last question. Let us thank Misao for his nice lectures. Okay. Okay, we will continue this lecture tomorrow at the same time in the morning. And
yes. All right. Okay.
Okay, you guys have a good days. Bye-bye.
Bye-bye.
Thank you very much, Misao.
Yeah. All right. Thank you.